When most people hear the speed of light, they think of it as just a very large number, an impressive record holder in a cosmic race. 299 million meters per second feels like a property of light itself, as if light is simply the fastest runner in the universe. But that picture is deeply misleading. The speed of light is not important because light is fast. It's important because that number is woven into the structure of reality itself. It is not merely a speed things happen to have, it is the rule by which space and time are stitched together. To see why, imagine stripping light out of the universe entirely. No stars, no photons, no electromagnetic radiation at all. Even in that dark hypothetical universe, the same speed limit would still exist. There would still be a maximum rate at which cause and effect could propagate. Something would still play the role that light plays for us. That's because the speed of light is not fundamentally about light. It is about space-time. In everyday life, space and time feel like separate things. Space is where events happen. Time is when they happen. You move through space, and time just flows along in the background, ticking away uniformly for everyone. That picture works well at slow speeds, so we internalize it and mistake it for how the universe truly works. But nature is not obligated to respect our intuitions. When experiments showed that the speed of light is the same for all observers, no matter how fast they are moving, something had to give. And what gave way was the idea that space and time are fixed and independent. The universe preserves the speed of light by allowing space and time themselves to stretch and bend. If you move faster through space, time slows down for you. Your clock ticks more slowly than one at rest. At the same time, distances along your direction of motion shrink. These effects are not illusions or measurement tricks. They are real, physical changes in how space-time is experienced. The universe does this automatically, relentlessly, and precisely so that everyone, regardless of their motion, measures the same value for the speed of light. This tells us something profound. The speed of light is acting like a conversion factor between units of space and units of time, much like how the number of centimeters per inch converts one way of measuring length into another. In relativity, space and time are not separate currencies. They are two expressions of the same underlying quantity. The speed of light tells you how much space corresponds to a given amount of time. It defines the geometry of space-time itself. Once you understand this, the idea of going faster than light stops making sense. It's not like trying to exceed the speed of sound or break some engineering barrier. Faster than light motion would mean stepping outside the structure that defines what before and after even mean. It would scramble cause and effect, allowing consequences to occur before their causes. In that sense, the speed of light is not a wall you crash into. It's the edge of meaningful physics. This is why the speed of light appears everywhere in modern physics, even in equations that have nothing to do with light. It shows up in relativity, in quantum field theory, in the energy stored in mass itself. It is the scaffolding on which reality is built. Light simply reveals this structure to us because photons, having no mass, naturally travel along the deepest grooves of space-time's geometry. So the speed of light is not just a number we measured and wrote down. It is the signature of how the universe is put together. It tells us that space and time are not passive stages, but active participants in the drama of reality. Once you see that, the speed of light stops being a curiosity and becomes something much more profound, the rule book of space-time itself. Before Newton, the universe was a place of separate rules. Things on Earth behaved one way and things in the sky behaved another. Apples fell straight down, stones arced through the air, and everything eventually came to rest. Meanwhile, the moon glided endlessly around the Earth, and the planets traced elegant paths across the heavens, seemingly untouched by the messy physics of everyday life. There was no obvious reason to believe these motions were connected. They looked like entirely different kinds of behavior, governed by entirely different principles. The breakthrough came from asking a deceptively simple question. What is the moon actually doing? At first glance, it doesn't look like it's falling at all. It just goes around the Earth, night after night, never getting closer. But imagine freezing the moon in place, removing its sideways motion. In that case, gravity would pull it straight down toward the Earth, just like a dropped object falls toward the ground. The only reason the moon doesn't crash into the Earth is because it's moving sideways fast enough that as it falls, it keeps missing. An orbit is not a state of balance or suspension. It is continuous falling combined with sideways motion. This insight alone was revolutionary, but Newton pushed it further. He realized that if the same force that pulls an apple to the ground also holds the moon in its orbit, then gravity must extend far beyond the Earth's surface. It must weaken with distance in a very specific way. Newton proposed that gravity follows an inverse square law. Double the distance and the force becomes 4 times weaker. Increase the distance by 60 times and the force weakens by 60 squared. This was not just an abstract idea. It made a precise, testable prediction. The moon is about 60 times farther from the Earth's center than we are standing on the surface. On Earth, objects fall a known distance in the first second. If gravity really weakens with the square of the distance, then the moon shoal, d, fall toward the Earth by exactly the amount predicted by scaling Earth's gravity down by that factor. When Newton did the calculation, the numbers matched. The moon was falling at precisely the rate required to keep it in its observed orbit. 2 facts that seemed completely unrelated, the way objects fall on Earth and the way the moon moves in the sky, were suddenly revealed as different expressions of the same law. That unification changed everything. Once gravity was understood as a universal force, the motions of the planets were no longer mysterious. Newton showed that an inverse square law naturally produces elliptical orbits, exactly as Johannes Kepler had measured decades earlier without knowing why. What had been empirical rules became consequences of a deeper principle. Even phenomena like tides, which had puzzled people for centuries, fell into place. The moon's gravity does not pull the Earth uniformly. It pulls more strongly on the near side and less strongly on the far side, creating 2 bulges of water and explaining why there are 2 high tides each day. The power of this framework was not just that it explained known facts, but that it could be trusted when something didn't fit. As measurements grew more precise, astronomers noticed small but significant discrepancies in the timing of Jupiter's moons. They sometimes appeared ahead of schedule and sometimes behind. Instead of immediately discarding Newton's law of gravity, scientists assumed the law was right and looked for another explanation. That confidence paid off. The discrepancy turned out not to be in gravity at all, but in light. Light takes time to travel, and the varying distance between Earth and Jupiter meant observers were seeing the moons as they were in the past. By trusting the gravitational theory, scientists uncovered an entirely new fact about the universe. Light has a finite speed. This was a profound lesson in how science advances. A single unifying idea can connect phenomena across vast scales, from falling stones to orbiting moons, and then serve as a tool for discovering even deeper truths. Gravity and motion were no longer local curiosities. They became the first glimpse of a universe governed by universal laws, the starting point of an avalanche of discovery that continues to this day. One of the most striking moments in the history of science came not from building a better instrument, but from trusting a law deeply enough to notice when reality appeared to disagree with it. By the late 17th century, Newton's law of gravitation had proven astonishingly successful. It explained falling objects on Earth, the motion of the moon, and the paths of the planets with remarkable accuracy. Astronomers began to apply it to more distant systems, including the moons of Jupiter, expecting the same precision to hold. What they found instead was a puzzle that refused to go away. Careful observations showed that Jupiter's moons did not always appear where Newton's equations said they should be. Sometimes they arrived about 8 minutes earlier than predicted, sometimes about 8 minutes late. This was not a tiny error that could be waved away. 8 minutes was enormous by astronomical standards. Even stranger, the discrepancy followed a pattern. When Jupiter was closer to Earth, the moon seemed ahead of schedule. When Jupiter was farther away, they seemed delayed. If gravity itself were wrong, there was no reason for the error to depend on the distance between Earth and Jupiter. Something else had to be happening. Old Romer approached the problem with an unusual mindset. Instead of doubting Newton's law, he assumed it was fundamentally correct and asked what other hidden assumption might be failing. The critical assumption turned out to be so deeply ingrained that few people had even thought to question it, that light travels instantaneously. When astronomers observed Jupiter's moons, they implicitly assumed they were seeing the events as they happened. Romer suggested a radical alternative. What if light takes time to travel? What if the apparent position of a moon is not its current position, but where it was some minutes ago? The idea immediately explained the pattern. When Jupiter is closer to Earth, light has less distance to travel, so we see the moons with less delay. When Jupiter is farther away, light takes longer to reach us, and the moons appear late. The 8-minute discrepancies were not failures of gravity at all. They were a measure of the time light needed to cross the vast distances of the solar system. By carefully analyzing these delays, Romer was able to estimate the speed of light itself. This was an extraordinary achievement. The speed of light was not measured by timing a flash across a laboratory or bouncing a beam between mirrors. It was inferred from celestial mechanics, from the motion of distant moons governed by gravity. In effect, confidence in one physical law allowed scientists to discover another. Gravity became a measuring stick for light. Without Newton's law providing a reliable prediction of where Jupiter's moons should be, the finite speed of light might have remained hidden for much longer. This episode revealed something profound about how science progresses. When a theory is truly deep and accurate, it does more than explain known facts. It creates expectations. When reality fails to meet those expectations, the discrepancy becomes a clue rather than a threat. Instead of discarding a successful theory at the first sign of trouble, scientists can use it as a lens to uncover new phenomena. The apparent failure becomes a doorway to discovery. The realization that light has a finite speed quietly transformed our understanding of observation itself. Every time we look at the universe, we are looking into the past. The sun is seen as it was 8 minutes ago. Distant stars are seen as they were years or centuries ago. Galaxies appear as they were millions or billions of years in the past. Observation is no longer a snapshot of the present. It is a time-delayed message carried by light across space. More importantly, this discovery set the stage for an even deeper revolution. Once the speed of light became a measurable quantity, physicists began to notice something unsettling about it. Unlike ordinary speeds, it did not seem to depend on the motion of the observer. That strange behavior would eventually force a rethinking of space and time themselves. But the first step in that journey was Romer's insight. By trusting gravity enough to question light, science uncovered a limit woven into the universe. What began as a small timing error in the motion of Jupiter's moons became one of the foundational facts of modern physics, showing how one law, firmly believed, can illuminate another hidden beneath it. Once the speed of light had been measured, physicists expected it to behave like any other speed. In everyday life, velocities add. If you throw a ball forward while walking, the ball moves faster relative to the ground than if you were standing still. If you throw it from a moving train, its speed combines with the speed of the train. This rule works so well in ordinary experience that it feels unquestionable. So when scientists began measuring the speed of light more carefully, they naturally assumed it would follow the same logic. It didn't, no matter how fast the source of light was moving, the measured speed of light remained the same. Whether the observer was standing still, moving slowly, or traveling at an enormous fraction of light speed, the result was always identical. The light never appeared to gain or lose speed. This was not a fluke of one experiment or a mistake in measurement. It was a consistent, repeatable fact, and it was deeply unsettling. If speeds are supposed to add, and light's speed doesn't, then something fundamental about motion must be wrong. Physicists tried to preserve common sense by imagining an invisible medium called the luminiferous, ether, through which light supposedly traveled. Perhaps light had a fixed speed relative to this ether, and different observers were simply moving through it. But experiment after experiment failed to detect any such medium. There was no preferred frame of rest. Light speed seemed to be the same for everyone, everywhere. Einstein took this strange fact seriously instead of trying to explain it away. He realized that the problem wasn't with light at all, but with our assumptions about space and time. We unconsciously assume that time flows at the same rate for everyone and that lengths are the same no matter how fast you're moving. These assumptions feel obvious because their effects are tiny at everyday speeds. But if the speed of light is truly the same for all observers, those assumptions cannot be true. Einstein's solution was radical but precise. Space and time are not fixed. They adjust themselves depending on motion in such a way that the speed of light remains constant. When you move faster, your clock runs more slowly compared to one at rest. This is not a psychological effect or a trick of observation. Time itself passes more slowly for you. At the same time, distances in the direction of motion become shorter. Space contracts. These two effects work together perfectly to keep the ratio of distance to time, the speed of light, the same for everyone. This idea overturns everyday intuition. Two observers moving relative to each other will disagree about how much time has passed and how long an object is, yet both will be correct within their own frames of reference. There is no single universal clock ticking in the background of the universe. Each observer carries their own time with them. What remains invariant, what everyone agrees on, is the speed of light. The consequences are profound. Events that appear simultaneous to one observer may not be simultaneous to another. Cause and effect become constrained by light's finite speed. Information cannot travel instantaneously, so there is a built-in limit to how quickly one event can influence another. This limit is not imposed by technology or by the properties of light itself. It is enforced by the structure of space-time. What makes this even more remarkable is that these effects are not philosophical abstractions. They have been measured directly. Atomic clocks flown on airplanes tick more slowly than those left on the ground. Particles moving ng near the speed of light live longer than they should according to classical physics. Satellites in orbit experience time differently than receivers on Earth, and their clocks must be corrected continuously to keep navigation systems accurate. Without accounting for time dilation and length contraction, modern technology would fail. The constancy of the speed of light forces us to abandon the idea of absolute space and absolute time. In their place, we gain a unified picture of space-time, where measurements of distance and duration depend on motion. But the deeper structure remains consistent. Light's unchanging speed is the clue that reveals this structure. It is the thread that ties space and time together into a single fabric. What began as a puzzling experimental result ends as a complete reshaping of reality. The speed of light does not conform to the universe we imagined. Instead, the universe reshapes itself around the speed of light. By insisting that this one number remain constant, nature tells us something extraordinary about how space and time truly work. As objects move faster and faster, approaching the speed of light, their behavior begins to diverge dramatically from anything we experience in everyday life. At low speeds, pushing an object makes it accelerate in a simple, predictable way. Double the force and you double the acceleration. There is no hint of a fundamental limit. But when speeds become a significant fraction of the speed of light, this comfortable picture breaks down. Acceleration becomes increasingly difficult, not because engines fail or fuel runs out, but because the object itself resists being pushed. This resistance is not caused by friction or drag. It arises from the geometry of space-time. As an object gains speed, its energy increases, and that energy contributes to its inertia, the tendency to resist changes in motion. In classical physics, mass is constant, so inertia is constant. In relativity, energy and mass are deeply connected. The faster an object moves, the more energy it carries, and the harder it becomes to accelerate further. This effect grows without bound as the speed approaches that of light. Early descriptions called this phenomenon relativistic, mass increase, suggesting that the object's mass itself was growing. Modern physics prefers to say that the object's energy and momentum increase while its rest mass remains the same. But the physical consequence is identical. The closer you get to the speed of light, the more force is required to gain even a tiny increase in speed. Each additional fraction of velocity costs disproportionately more energy than the last. This leads to a striking conclusion. To accelerate an object with mass all the way to the speed of light would require an infinite amount of energy. No matter how powerful your engine or how long you accelerate, you can get arbitrarily close but never quite arrive. The speed of light is not just difficult to reach, it is unreachable. The universe does not merely discourage crossing this threshold, it makes it impossible. Light itself behaves differently because photons have no mass. For them, the speed of light is not a limit to be approached, but a state that must always be maintained. They cannot slow down or speed up. They simply move at that rate forever. This sharp distinction between massless and massive particles is a direct consequence of space-time's structure. The rules are not imposed externally. They emerge naturally from how energy, momentum, space, and time fit together. Another way to see this limit is through time itself. As an object moves faster, time slows down relative to the rest frame. At everyday speeds, the effect is negligible. At relativistic speeds, it becomes dramatic. If an object could somehow reach the speed of light, time would stop entirely for it. But reaching that state would require all of the object's motion through space-time to be converted into motion through space, leaving none left for time. That transition cannot be completed. There is no way to have less than zero motion through time, so the process halts before the speed of light is reached. This is why the light speed barrier is fundamentally different from any other limit we encounter in nature. It is not like the maximum speed of a car or the strength limit of a material. Those are practical limits that could, in principle, be overcome with better engineering. The light speed limit is woven into the rules of causality themselves. Allowing massive objects to exceed it would mean allowing effects to precede causes, breaking the logical structure that makes physics possible. Experiments confirm this picture with astonishing precision. Particle accelerators push electrons and protons to speeds within tiny fractions of the speed of light. As predicted, each increase in energy produces smaller and smaller gains in speed, while the particle's energies soar. No experiment has ever observed a massive particle reaching or exceeding light speed. Every test reinforces the same conclusion: the closer you get, the harder it becomes, and the wall is never breached. The speed of light, then, is not a rule imposed from outside the universe. It is the natural outcome of how space-time responds to energy and motion. Objects with mass are forever confined below it, not by lack of ingenuity, but by the fundamental architecture of reality. The universe itself enforces the limit, quietly and absolutely, every time something tries to go faster. At the deepest level, the speed of light is not about light at all. It is about how cause and effect are allowed to unfold in the universe. Every event that happens can influence other events, but that influence cannot propagate arbitrarily fast. There is a maximum rate at which information, forces, and changes can spread. That rate is what we call the speed of light. It defines the boundary between what can be causally connected and what cannot. In EV, everyday experience, this limit is invisible because it is so high compared to the speeds we encounter. We flip a switch and a light turns on, and it feels instantaneous. We speak and are heard almost immediately. Cause and effect seem tightly bound, but at larger distances or higher precision, the delay becomes undeniable. Light from the sun takes minutes to reach Earth. Signals sent across space take measurable time. The universe does not update everywhere at once. It has a built-in speed for the propagation of now. This limit forces a particular structure on space-time. Events can be represented as points in a four-dimensional fabric, with 3 dimensions of space and 1 of time. From any given event, there is a region of space-time that can be affected by it, and a region that can affect it. These regions are bounded by paths that travel at the speed of light. Anything outside those boundaries is causally disconnected. No signal, no force, no information can cross that gap without violating the fundamental order of cause preceding effect. Once this structure is in place, faster-than-light motion becomes more than just difficult, it becomes incoherent. If information could travel faster than the speed of light, different observers would disagree about the order of events in a way that allows contradictions. An effect could be seen to occur before its cause. Messages could be received before they were sent. The very idea of a consistent history would collapse. The speed of light protects the logical consistency of the universe. This is why the speed of light appears not only in relativity, but in every theory that respects causality. It is the speed at which fields change, at which influences propagate, at which reality communicates with itself. Light simply rides along this structure because it is massless, but the structure would exist even if light did not. Gravitational waves, for example, also propagate at this same speed. The limit is universal. Another way to understand this is to think of space-time as having a fixed budget of motion. Every object moves through space-time at a constant total rate. If it is not moving through space, it moves entirely through time, aging 1 second per second. As it begins to move through space, some of that motion is diverted away from time. Time slows down. The faster the spatial motion, the less motion remains for time. This trade-off continues until a maximum is reached. At the speed of light, all motion is through space and none is left for time. From this perspective, time does not pass at all. This is why massless particles experience no passage of time between emission and absorption. But going beyond this would require negative motion through time, which has no physical meaning. There is no